yourself, what can the local structure of the foliation be, given that there's one of these things? And you find that, if you perturb this thing just a little bit inward, you have to have a closed trajectory. I couldn't instantly prove it. You can find this kind of stuff is, for example, in Strebel's book on quadratic differentials. All this stuff is explained.
Because it's measured, right? So there is this transverse measure, right, which is.
It's a measurable foliation. So it's reasonable. But why do you have another one?
Oh, why do you have another one? Well, you have to ask yourself, how can that family end, right? It has to terminate somehow.
Oh,
so
no, this was his remark.
So that's right. So strictly speaking, there's another possibility which I forgot about because, but it pretty much has to be either this or this. You might think that it could end on something fancier, as I said, but let me just say it again. You might think it could end on something fancier like that, right? But in this situation, there would be two different gammas that are appearing at the same value of theta. And so I've forbidden that by putting this condition. Okay, so this is my definition of the invariants omega of gamma. So they depend on my quadratic differential, but they don't depend on anything else.
To be sure that we understand the definition, the endpoints should be saddles, or they could also be singularities at double poles.
The endpoints of what? Oh, the endpoints of the trajectory?
Yeah.
Oh, yeah, sorry. These things that I'm drawing, they're always things that have ends on the zeros, not the poles. Yeah, I mean, okay. Let me say a word about the poles. So what's the nature of the what's the nature of this foliation around the poles? So good. Yeah, I should have drawn it right here, but I didn't. So around the poles, what happens depends on the residue. So for generic, at generic theta, what happens around the pole is that the trajectories kind of spiral in. So you get that just by integrating this differential equation. So they're like attractors. They're kind of attractors for these trajectories. And actually, that's roughly the reason why these things make the analysis so much simpler, is because the analysis is complicated mostly because of the possibility of trajectories that run all around the surface in some crazy way. But if you have these poles, then they restrict the possible behavior, because when the trajectory comes close to the pole, it'll spiral. So for generic theta, this is what happens. Then there's one special value of theta, or I guess two special values of theta, determined by the residue at the pole, where you actually get closed loops going around. And that's the situation that Maxime is reminding me to worry about over there. So there's a lot of trajectories going into any given singularity. But, so it would be very generic, to ask for a trajectory that just goes from one singularity to another. There's a million of those. But there's very few trajectories. Each of these supports only 3 trajectories, and so these saddle connections are those special ones, the S ones. Okay. Okay, so those are omega gammas. They're supposed to be examples of Maxime's story.
But we define omega to match the story of the morning. There is no a priori reason to define them like this.
We will encounter a reason. Yeah, a pretty good reason is that the wall crossing formula will be obeyed exactly with this assignment of omegas and with no other reason. Historically, the reason why, at least I, Gaiotto, and Moore thought about it actually came from physics. There was some physics reason why those were the right numbers. But yeah, I think for our purpose, it's the wall crossing formula. Okay, good. Well, of course, in principle, you would say that it just comes from doing the counting, so to speak, correctly. Yeah, okay, maybe I can say a word or two about that. So I mean, we had this discussion this morning about these special Lagrangians, and we said if they're isolated, then they always contribute equals 1. But this thing is isolated, and so it's somehow correct that it contributes equals 1. Now here, these two guys are sort of sitting on the boundary of some moduli space. There's a moduli space. This corresponds to a special Lagrangian of topology S2 times S1, so just as Maxime says, it has one modulus, and that modulus is this sort of distance. And so you have to somehow figure out the contribution from that family. The claim is the correct contribution from that family is -2. Okay, that I couldn't prove from first principles, but if you're really good at doing the sort of moduli space analysis and Donaldson-Thomas theory, maybe you can get it from first principles. Okay, so so I've defined these things. So it's 1 if there's a saddle connection, minus 2 if there's a closed geodesic. And of course, if gamma is a charge which supports neither of these things, then the invariant is 0. So now I've defined all the invariants. So now, there's this wall crossing. And the phenomenon of wall crossing is just that as we vary phi 2, these integers, omega of gamma, to emphasize they depend on phi 2, let me write them like this, they may change. And the way that they change is exactly that special trajectories can appear or disappear. So if you like, let me define B to be the space of these meromorphic quadratic differentials, phi 2, and there's literally some loci in here where the omega of gamma is jump.
Do we only vary phi 2 without varying conformal structure?
Okay, in principle you could also vary the metric on the curve. Everything will be exactly the same. For some reason I tend to think of keeping the curve fixed, but it's absolutely not necessary. Right, and you can also vary the residues for that matter at the poles, just as long as you don't make them 0. So why does this wall crossing happen? So now I hope I can show you some pictures. So let's see. So let's see. I pushed the on button, but it doesn't.
Yeah, it's.
Oh, it is. No, yes, it is. Okay. So while it warms up, I can say a few words. So of course, the picture that I'm going to show you is going to be exactly the picture that Maxime was drawing of 2 special Lagrangians that intersect each other and they make a third special Lagrangian. But I show it to you in the context of these special trajectories. So here I've just plotted the actual I've chosen some particular quadratic differential and I've just plotted these leaves. So here's a singular point. I'm drawing the 3 S walls coming out of that singular point. So as you vary this phase parameter, these walls just rotate. So that's sort of the local structure around each singular point. Now what we're supposed to do to see these special trajectories is we're supposed to vary that parameter through the whole range of 2 pi and look where the special trajectories occur. So let's see one of those special trajectories. So here's the next simplest case where I have just two of those zeros. I have just 2 of these zeros. Now it's possible to have one of these special trajectories appear, and indeed, as I vary the phase, the S walls are rotating, and at this critical moment they hit each other. So now you see there's exactly 1 saddle connection in this example. So this would correspond to an invariant omega of gamma that equals 1. And you notice something else about this, which is even if you don't have sort of infinitely good resolution in your analysis, you can still detect that this thing has occurred. Even if you don't see it exactly at the critical moment, you nevertheless can see it because there's kind of a topology change of the S walls, right? So the S walls here, they're configured in one way, and right after the thing, they're configured in a different way. So that's actually going to be, the way we're going to analyze these objects is not so much to look at the object itself, but to look at this topology change of the S walls. Okay. So this example, there's still no wall crossing. I'm just showing you a single quadratic differential and finding the single saddle connection at that particular quadratic differential. So now I want to show you the wall crossing phenomenon. So this is an example with now three zeros here, here, and here. And so this story has a sort of interesting modulus in it, where I vary the relative positions of those 3 zeros. And if I do that while holding the phase theta fixed, you can see that one of the zeros just moves up and down, and so the picture changes a little bit. Now suppose that I now look here and I ask what are the saddle connections going to be? Well, you might guess that there's going to be a saddle connection here and a saddle connection here. And sure enough, that's what's going to happen. So there's one of them. And if I vary a little more, there's the other one. So two saddle connections. And they're two saddle connections which intersect each other at one point. Right? Because they have this middle point in common. So if I look at their lifts up to the first homology, the intersection number between these two things is 1. So it's just like Maxime's situation of two special Lagrangian 3 spheres that have intersection number 1. So this corresponds to one point in so that was one particular point in parameter space where I had, let's say I'm on this side, I had two charges, omega gamma 1 equals 1, omega gamma 2 equals 1, but nothing else. All the other charges are 0. Or if you like, strictly speaking, if I go around 360 degrees in the phase, it's natural to also say these two are 1. But there's basically nothing else. So now I'm going to vary the parameters, vary my quadratic differential to this other place. And now at this place, the three things look much more symmetrical, and you could imagine there's going to be a third thing. And there is, so let's see, so now you find 1, 2, 3. So evidently there was some moment where we've crossed a wall here. The invariants were so now this is 1, this is 1. But also, and if you look at the homology classes, it's sort of clear that that third one has homology class gamma 1 plus gamma 2. So there must have been some moment at which something special happened. And let me see if I can sort of zoom in on that exact moment. I think maybe it's here. So, yeah, so you know, when you get very close to the wall, it's somehow hard to tell whether there's 2 or 3. And the way you see that, you know, look at what the picture is here. So kind of everything's happening at the same moment. So, you know, there's pretty clearly one there, and there's pretty clearly one there, but it's somehow very hard to see whether there's one here. And somehow the reason for it is exactly that, so, you know, you had one which went like this, and it's kind of become singular. It's decayed into the union of these other two. And the way that it happens, the moment at which it happens is a moment when all three of them have the same phase, right? They all appeared at the exact same moment on this picture.
So is it 120 degrees?
Is it 120? I don't think so.
But don't we have 120 for each
vertex? Yeah, of course. Yeah.
Sorry, you're saying that this is 120 degrees?
Yeah. In the conformal structure, yes.
Yeah, no, sure. Okay, I can't instantly see that it's 120 degrees.
No, in conformal structure.
Oh, it's always 120. Yeah, sorry. Sorry, that's right. The angle between any two S1s is always 120 degrees. Yeah, sorry. Yes. Right, okay, great. So that's this wall crossing phenomenon. That's the example that Maxime described. And we're going to see in a minute that that's an example of Konsevich-Schlegelmann's wall crossing formula. But let me show you a sort of fancier example, because that one maybe, you know, you wouldn't get super excited if that was all you could do. So to get something a little more interesting, we have to find some example. That actually has these. Oh, this is mostly. Maybe with the lights off, it's better. Yeah. Okay. We have to find some example that actually has the closed geodesics. So let me look at this one. Let's see. So this is a picture of a cylinder, which has and a quadratic differential which has 2 zeros. So there's one here with 3 lines coming out of it, and one here with 3 lines coming out of it. And what's happening is that all the trajectories are, you know, ending up all the way down the cylinder here or all the way down the cylinder up here. So now I'll do my usual thing. I'll just vary the phase and see how many closed trajectories I find. And what I will find, let's see, nothing there. Okay, at this moment, there's a closed trajectory. No, sorry, not a closed trajectory. There's a saddle connection that goes from here to here. So that's one saddle connection. And now there's going to be another one going the other way around the cylinder. Right, yeah, there. So here's another thing. So it's a lot like the situation I showed you before. I just have two saddle connections, but with one crucial difference. now the saddle connections have both endpoints in common. Before they just had one endpoint in common. So this is two saddle connections. Now with if I lift them up to the cover, the intersection number of those charges is 2, not 1. So before this was the case. This was the case where the intersection number was 1. And now I'll just be here for a second. And now I want to draw a similar thing, but where the intersection number is 2. So again, I'm going to be in the situation where omega gamma 1 is 1, omega gamma 2 is 1, but this time the inner product of gamma 1 and gamma 2 is 2. And now we ask what happens when I vary things so that their phases align. Yeah, I said it, but maybe I didn't emphasize it. So this wall is exactly at the location where z gamma 1 over z gamma 2 becomes real. And here, similarly, the wall is going to be where z gamma 1 over z gamma 2 is real and positive. So what happens on the other side? Well, let's just look and see what happens. So now I vary my parameter. So now varying the parameter means moving these two zeros sort of away from each other on the cylinder. And now I should find a more interesting structure. So what do I find? Well, for a while nothing happens. Okay, right there is a closed, right there is a saddle connection. So there's at least one there. But now they're winding more and more tightly around the cylinder. So there's actually many saddle connections here that I'm not seeing because these two curves are winding more and more around the cylinder and they hit each other many times as they do. So in fact, right, more. And then there's this one critical moment. So the thing winds around more and more and more. There's actually an infinite set of those saddle connections there. And then there's this critical moment where I get closed trajectories. So actually, although I'm not plotting them, there's a whole cylinder worth of closed trajectories here between these two. So according to my rules, so this corresponds to a situation where, and if you check, the charge of that one is gamma 1 plus gamma 2. So omega gamma 1 plus gamma 2 is minus 2. And there was a whole pile of the ordinary saddle connections, which, if I get it right, is n gamma 1 plus n plus 1 gamma 2 is 1. And also the other way, n plus 1 gamma 1 plus n gamma 2 is 1. So over here you had just two non-zero invariants, and over here they formed an infinite number of bound states. Almost all of them with 1, and there's just one special guy with minus 2. Okay. And let's see. Oh, this picture is just looking a little more closely at that infinite set of saddle connections. So you can see these things are sort of winding around, and they hit each other infinitely many times. All right, just on that. And then eventually get into that. Okay. Okay, so that's it for the pictures for now. Okay, so those are some examples of wall crossing, and I guess the next thing I want to explain is how precisely this is an example of Maxime and Jan's wall crossing formula, Thiebaud-Schoenfeld wall crossing formula, but I guess I should do that after we have some break, right?